In this video, I'm going to describe the binary search. The binary search is an efficient search because we can use recursion to give it big O log n algorithm growth rate, which is a fairly efficient growth rate over a large set of data, because what that means is we add more data to our list that we're searching across, it is going to take more time to process, but that time that it takes to process is going to be increasing at a decreasing rate. In other words, the curve is going to flatten out, or get more flat rather, as the data set grows, and this gives us a bit of efficiency as we're trying to search a large data set. So let's think about an example. Let's say that you wanted to find Brandon Jones in the phone book, and actually I don't know if I exist in the phone book or not. They dropped a whole bunch off downstairs, but who uses a phone book anymore? But nonetheless, that's an aside. So let's say you need to find Brandon Jones in the phone book. How are you going to do this? Are you going to start with the first page with Aaron and read every single entry until you get to Jones Brandon? That would not be efficient, and that's not how we work as humans. What we would do more than likely is open the phone book about halfway and see if we've passed the Jones or we're before the Jones. If we've passed the Jones, then we take that first half of the phone book and we open that up halfway. And then once again, we do the same thing. We say, okay, am I past the Jones or am I before the Jones? And we keep doing that until we find Jones, and then we find Brandon Jones. That is recursion. So we're taking a big problem, which is the whole phone book. We're making it simpler. And then we continue to make it simpler by applying that same formula until we get our result. Now, the caveat is that list has to be sorted. That's how that phone book search works, because it's in alphabetical order. And actually, I will cover sorting in a different video. We'll talk about bubble sort, selection sort, and merge sort. And it's funny because merge sort itself also uses recursion. And in that case, it gives us O(n) times log n performance. And so we see that we can use recursion several times here to make algorithms that are efficient across a large set of data. Now let's take a look at this with an animation. I've created a sorted list of numbers, and I want to find a specific number, so I'm going to continuously cut this collection in half. And what I'm showing in this animation is the half that I'm interested in. I'm changing the color on these numbers, or actually the background behind the numbers. The ones I'm discarding, I'm not changing the color. So take a look at what gets accessed and what does not get accessed. So here's my list. There are 14 numbers in the list, and I need to find the number 37. Now we know it would be inefficient to start at the beginning and look at every single number, especially as this list gets long. So let's do the approach where we keep cutting it in half. So we start around the point where we have 7 numbers, and you see those have colored in red, those last 7 numbers. And it's sitting on the border of 25 and 26. We know it's sorted. We know we need to find the number 37. So we're going to take the right half of this collection, and we're going to cut it in half again. And you can see from 37 on to 63 that those are colored gray, meaning we're now interested in this part of the collection. So now we're going to cut it in half again. And that's going to leave us with 37 and 43, which now have a green background. And now we need to cut that in half just one more time, and boom, there is our number 37. So you can see that recursively, we're taking this problem and we're making it smaller each time. Specifically, we're making it half as big as it was the last time, and that's recursion. We're applying the same formula and making a simpler problem. So if you were counting there, you can see that the elements we tested were essentially 26, 31, and 37. 1 through 25 we never touched. We just had to find that midpoint, and that's it. And then there were several elements that we discarded without accessing them directly. 29, 37, 43, 54, 63, and those are your lottery numbers for today. Now, because we're constantly cutting the list in half and discarding it, this binary search becomes a very efficient operation because it's easy to just cut the list in half and discard half of it. And as the list grows in size, it will take more time to process the list, but that growth is increasing at a decreasing rate. So said another way, every time we cut the list in half, every step where we cut the list in half allows us to double the size of our list, and that gives us this powers of 2 equation that underlies our logarithm. that concept of doubling our list every time we add one more unit of time, or every time we cut in half one more time, is very powerful. I've created a little table here to help demonstrate this. So this is the size of the list, the power of 2, and the maximum times you would need to cut in half to find a specific item, worst case. If we have a list size of 1, you don't have to cut it in half at all. And what we'll find is that list is essentially 2 to the power of 0, or 1. Now, if we have a list of 2, then that's 2 to the power of 1, and at worst case, we'd have to cut the list in half once to find our item, right? We just cut it right in the middle. It's either to the left or to the right. Now, here's where things get cool, is when we get to the higher powers of 2. So if we have a list size of 4, that's 2 to the power of 2, and at most, we're going to need to make 2 cut in halves to find our item. So maybe cut in half here, then cut in half here, then it's either to the right or to the left. Now, we continue with these powers of 2. So 2 to the power of 3 is 8, so that's the maximum size of our list, and that requires 3 cuts to find our item, worst case. 2 to the 4th, 16, 2 to the 5th, 32, 2 to the 6th, 64, 2 to the 7th, 128. So you see, as we start saying, okay, worst case, I'm willing to do 7 cuts in half, the size of our list increases dramatically over the first few times, the first few items we had in that collection. So this is how we get to that logarithmic curve, and maybe you can start to visualize it when you see 1 cut is, or 0 cuts is 1 item, 1 cut is 2 items, 2 cuts is 4 items, 3 cuts is 8 items max, and I'm saying that's the max size that list could have. You can kind of start to visualize what this curve is going to look like. So let's take a deeper look at what a logarithm is. The exponent or power to which a base must be raised to yield a given number. That definition is a little bit tricky for me, but if we see it on a graph, it's going to make a bit more sense. So with big O notation, we're typically talking about a base 2 log. So 2 to the power of x is what? Or this number is 2 to the power of what? Okay, this number is the number of items in our list. So 1 is 2 to the power of 0. 2 is 2 to the power of 1. 4 is 2 to the power of 2. 8 is 2 to the power of 3, and so on and so forth. 16 is 2 to the power of 4. So you can see how this logarithmic function is increasing time to process as our list gets longer, but the increase is increasing at a decreasing rate. So in other words, that curve is flattening out, because essentially every time we double our collection, it takes only 1 more unit of time to process that collection. And that's how recursion and a bit of binary math can give us this log n performance, which is a fairly scalable performance unit as the number of items in our list increases. So as always, I hope this video was helpful, and I look forward to reading your comments. Thank you.